the IBG307 student. Okay, so today is my part. I will show you how to do RSM, or the optimization using the R software. Okay, so same as a design expert, we will use RSM method for optimization, but now I will show the RSM method using R software. Okay, so first thing, you have to download these three R downloader. So this is a R project, R studio, and the R tools. So you need to have these three to proceed with the R. Okay, so here the R studio, we have the console here, and then environment. Okay, this console is where we'll key in all the coding. Okay, and the environment is where our data will be located. Okay, so any coding we need to key in here, console. And then if you want to install any package, so you have to click tools, install packages, and then just key in any name of packages. For example, we need RSM. If I have this data is okay, I want to know the interaction, the effect of propanol concentration on the pHa. So this propanol, we have three types. This 0.8, 1, and 1.2 gram per liter. So then the each 0.8, 1, and 1.2 the experiments done with triplicate. Okay, so that's why I have 3 times here, and then this result for the pHa. Okay, first thing, you have to key in this data with the header in the Excel, and then save as text.txt. Okay, so this tree is the coding. I will show how to key in into the R studio. Okay, first I will show how to key in the data in Excel. Use the simplest name, so it can be easier to be called in R studio. So propanol, just I write prop, all the capital letter, and then pHa. And for your information, okay, if we want to do ANOVA or t-test, you have to remember during our IBG307, I'm not sure whether you have taken the IBG307, but if you remember, for the t-test and then the ANOVA, one-way ANOVA, so you have to let the parameter, the independent parameter, the value as a different letter. Okay, 1, 1, 2, 2. But this time I use A, B, C, C. So A is 0.8, B as the 1, and C as 1.2. Okay, so for one-way ANOVA and t-test, you have to change the independent variable as a letter, as a group. Okay, as a group. Because if you remember, in the SPSS, we change using the label. Okay, the group. If you have group, you have to change into a letter of group, A, B, and C. Okay, then I key in the data into the Excel. Okay, with a header, and then you save as. So you can take text. Okay, then save in a file that you will use for the that you will use for the R software. Okay, save in one file. Okay, save in one file, so just save it. Okay, because I already saved before this. Okay, and then in R studio, to call that file, so you have to key in this. Okay, so you have to key in this into RStudio. Okay, you have to call the file. Okay, so this is the link for the file. Okay, where to get this link? Okay, so this one is just a name, fn data. So any name you can put. Okay, so example, I key in into the console of RStudio. Okay, this one where you can get, you go to where your file that. Okay, so you find where you save your file. So that file name I save as prop. Okay, so I go where the prop txt prop text located. So go to that file and then right click, then click on properties. So you can take the location here, this. Okay, so you, okay, but all the forward backslash has to change to backward backslash. Okay, for RStudio you have to change this backslash, and then as you can see, this is my file name. Okay, here my file name, my location name, but then you have to add on what is my Excel, my text propanol concentration name. So my propanol concentration name is I save as prop. So we have to on the name of our text file dot txt. Okay, make sure we have dot txt. So this is our text file name where our data is key in. Okay, and then just click OK. After that, you have to read the table inside the file. So that's why we have this coding read table, fn data, read this, and the header is true because we tick the header. And then this in front is just a name. You can put either propanol, p, just a name for this read table. Okay, so then I copy this coding into RStudio. Okay, then click OK. So we already read the table. So as you can see, we have 9 objects of 2 variables. So we want to make sure that it's you get a correct table. You can key in this name. Okay, call back this name. So this is our table from the Excel. Okay, thing you have to do is to screening all the parameters that you have using one-way ANOVA. So you have to screen whether that all the parameters are significant or not, because for the optimization you have to continue with the significant parameter. So the insignificant parameter you can eliminate. Okay, so first you have to screening using one-way ANOVA. Okay, I will show how to do one-way ANOVA in RStudio. Okay, so you use the same data, same file of data prop. That's why, okay, this one is just a name, ANOVA prop. So you can just state ANOVA 1. Okay, so this the coding for ANOVA in R, AOV. Okay, then bracket. Okay, so this one is the name of dependent variable. So our dependent variable is PHA, independent variable is propanol. But you have to write down the name as what you key in the Excel file. Okay, so I key in as a capital letter of PHA and then capital letter of prop, PROP, and then we have data equal to the name of the read table that we have, prop here. Okay, yeah, data, the read table name. Okay, so I copy this one. Okay, as you can see the table here, PHA, prop, capital letter, prop, and the data name is the name of the read table. Okay, and then this one you can put any name. Okay, then click OK, and then you want to know the result of the ANOVA. You have to put summary and then the name of the ANOVA coding here, ANOVA prop. Okay, so we have this summary, the summarization of ANOVA. So we want to know whether it's significant or not. You look at the p-value here. Okay, 0.0329 is less than 0.05. So when the p-value is less than 0.05, that means that the independent variable has significant effect on the dependent variable. Okay, a significant effect. So that means this one is less than 0.05. That means that propanol, different types of propanol have significant effect on the PHA. Okay, different propanol, different types of propanol have effect on PHA because it's less than 0.05. That means this parameter is significant. That means you can continue with the optimization. Your point? Yeah. So we can continue with the optimization. Okay. So first thing, you need to continue with the experimental design, whether to use the box beacon or the CCD. I think Dr. Tan already brief you about what is BBD, what is CCD, or you can find by yourself which one's better. But for me, I will tell you that CCD is better because it show more run order that you can have, because when we have more run order, more experiment, more accurate your result. Okay, so we continue with the significant parameters. So example, if the propanol we have one more parameter, molasses concentration, and that molasses is significant because propanol we already know that significant from the ANOVA. And then if you want to test with the molasses, you can try this data. Okay, so molasses also significant. So we continue with the simulator and then we select the experimental design. So I will choose the CCD. Okay, this experimental design because it will give a design of experiment that you have to do in your lab. Okay, so they give run order with the design of experiment that you have to continue to do in lab. Okay. Okay, first thing you have to call the package because if you first you have to install the package RSM. So install the package. So you put RSM and then click. Okay, so after you have done, you can call the RSM. Okay, call the package RSM. Okay, and then so for CCD, this one is just a name. You can put as DE or you can put as CC, any. So this I put as design experiment DE. Okay, and then CCD, this is our coding, and then these two is mean as there is two parameter, so 2 here, and then O and 0 equal to 1 mean that there will be repeated value for the center value. Okay, first thing to run this, okay, you have to take the highest PHA yield, where the parameter that take the highest PHA yield. So for the molasses, so we go to the molasses, we have the highest yield 1819 is at 40. Okay, that's why we have 40 here. Okay, and then for the propanol, the highest yield is at 0.8. Okay, value, so you have to take the difference. Okay, whether you want to, the difference is 2 between each 40. Okay, this is the middle 40. Whether you want to take the difference is 2, so it become 38, and then 42. So I take the difference between the center. So this the highest is the center. Okay, so the highest is called the center. Then we need to take, so okay, the highest one 40 is the center, so we need to take the negative side, the positive side. So negative side and positive side must have the same difference. Okay, so this one is the highest, and then this one is the difference between the negative side and positive side. Okay, and then propanol, so I take the difference is 0.5. This the form of the in mathematical form of this coding. So molasses minus 40 divided by the difference. So parameter minus highest divided by the difference. Okay, same as 0.8. I take 0.5. That's why negative side is 0.3, and then positive side is 1.3. Okay, this what I mean. The center 40 and 0.8 is repeated by 1. Okay, or 1 times only. Okay, so you want to repeat it twice, so you can put 2 here. Okay, so this list you have to put all the parameter that you have. So I have already 2 parameters, so x1 and then x2. So each parameter have to put this type of equation. Okay, so mole minus 40, and then prop minus 0.8. Okay, so this one more. So name, I use the lowercase here, new. So I copy into the RStudio. Okay, and then we want to see the result of the CCD. Just click in the name here, and then we get this result. Okay, so as you can see, we have more molasses propanol, and then we can see that this the design of experiment that CCD give. Okay, so we will do molasses 45, and then propanol 0.3. Then you got the PHA yield using the by hands-on lab. Okay, so CCD will give you all this new data with the different in the highest. Okay, so then you have to continue with the lab work. Okay, So you have to do for each this 10 run order. So the CCD already give you all the 10 run order. They have to do this 10, and then you have to do duplicate for each 10 run order here. Okay, so you have to follow 47 molasses, 0.8 propanol, and then get the pH A. Okay. Okay. So this result from the R. Okay, and then after you do the lab work, okay, so you get the pH content for each run order. So we have 10 run order, then we have 10 pH content. So make sure after you get the CCD, you do the experiment, do the lab work, duplicate, and then get the average for the pH content for each run order. Okay. Next, we will fitting RSM. After you get the result of your dependent variable, you have to fit a RSM, a model, whether it's second order, quadratic, or linear model. Okay, so this form of the linear model, linear multiple regression model. Okay, so we have the linear interaction and then quadratic. Okay, so to fit the second order linear model in RStudio, so you have to change this independent variable into the decoded data. Okay, to get this decoded data, we will use back the equation of difference, okay, for the molasses of propanol for each parameter. Okay, to get this -1, 0, that's why I mean that we have negative side, positive side, and then the center, the 40, the highest one is 0, because 40 minus 40 divided by 5, so you get 0. Okay, so 35 minus 40, you get -5 divided by 5, that's why you get -1. Okay, then 45 minus 40 divided by 5, that's why you get 1. Okay, so you can use the Excel formula, key in this formula, whereas this column minus 40 divided by 5, so you can get this. Okay, so you have to change to the decoded data for to fit the second order, to fit the linear model. Okay, so I will show. So if we have this, okay, I key in into the data, the uncoded, so I save as second order, the name. Okay, to get the decoded, you can just key in the formula. Okay, this for the molasses, okay, this one minus with the highest one, divide by the different, okay, 5, so you get -1. So same as others. Okay, just drag it. Okay, this is for the molasses and propanol. Minus 0.8 divided by 0.5. Okay, so you get -1. Okay, so this is the same one. Okay, so this decoded data. So you copy this one into the new Excel. Okay, so new Excel with the header. Okay, so more props, so I use the lowercase phe. So this decode data. Then I save as txt name decode. Okay, don't forget all the data I have to key in. I have to save as txt text. Okay. Okay, first thing, same as previous, you have to import the decoded data. So you have to call back the file. So same using the fn data and then the location and the file name decode.txt, and then you read the table. Okay, you can just copy this to the R Studio. Okay, so to make sure you get this correct table. Okay, wait. So we have this -1, -1, 10. Okay, all this. So that's mean you have the correct table. -1, 1, -1. So then for the second order model fitting, so this time we use the RSM. Okay, so we already called the library RSM. This one is just the name, and then RSM. Okay, and then formula, this one, and then this then our header in the SL file, SL text file. So PHA SO is a second order, and then this our independent variable mol and prop lowercase, because of I save as lowercase in the Excel file, and then the data equal to what's the decoded file name. So because I've saved as decoded, save as secoder for the read table here. Okay, so I copy paste this into the okay. So as you can see, PHA, and then second order more. Okay, so we can just use this coding but change the parameter if you want to try for the other experiment. Okay, and then data, this is our read table name. Okay, and then click OK. So we want to know the summary of this RSM, so just summary, and then take this name. Okay, so we have this full summary. So as you can see here, okay, I will take this table first. I will show it for this table first. Okay, this is the first result, first part of this result of RSM. Okay, as you can see, we have this first parameter, molasses propanol, then this molasses and propanol interaction, molasses square quadratic, propanol square quadratic. Okay, and then this is a p-value. Okay, this one, as you can see, the result, all these results are significant because it's less than 0.05. Okay, and then when we have this, that means all the interaction, all the quadratic and the linear are significant. Okay, and then we have to form a second order linear model with the significant result. Okay, so all these are significant. That means we have to put all into the model. Okay, so this is the first one, the B naught, we take intercept, and then we continue with the linear. First x1, because we have two parameter only, so we take x1, x2. If we have another parameter, so we have to add on plus x3. Okay, same as interaction. So if we have x3, so you have to wait and make x1, x2, x2, x3, then x1, x3. Okay, so then we have x2 1.37, and the interaction negative 0.45, and then square x1 square S2 squared. So because I have 2 parameters, so just S1 S2. If you have 3, so you have to add on S3, the third parameter. Okay, and then you have to put the significant only. If example this interaction is not significant, so you have to eliminate this. Okay, so you have to eliminate the negative 0.45 interaction. Okay, if the square propanol is not significant, so no need to write down the value of the propanol square. Okay, so just put a significant result only. Okay, and then the second part of the RSM result, we have the name as analysis of variance table. Okay. And then the second part of the RSM result, we have the analysis of variance table. We have this FO, TW, PQ. Okay, so FO is the first order, the linear, molasses and propanol one by one, and then 12 TWI is the two-way interaction. PQ is the pure quadratic. As you get from the previous, all the interaction, first order, quadratic is significant. That's why the p-value here also significant, less than 0.05. And then one more that you can conclude for the model, you can look at the lack of fit. Okay, the lack of fit, if this p-value of lack of fit is more than 0.05, not significant. It's not significant. Okay, it's not significant mean that the model fits well. Okay, the lack of fit can tell whether that the model is a poor or the good model. Okay, so when the p-value of the fit is more than 0.05, not significant, that means that the model is correct. The model is fit and can use for this experiment. Okay, so make sure you check the lack of fit. Okay, so if the lack of fit is significant, that means that model is wrong or cannot be used in this experiment data. So you have to do the data again, and you have to do the experiment again. Okay, maybe there's something wrong with your data. Okay, so make sure you get the lack of fit is more than 0.05. Okay. Okay. To know whether that model is fitted or not, you can also use all this histogram. Can compare the R square. This we use the lack of fit. Okay, you can use then you can use the contour plot. For this class, I will not show the contour plot. Maybe if you want to know, you can try to find it, how to do the contour plot, and maybe if you want to know more during your FIP later, you can meet me during your 4th year. Okay, so this all this contour plot, all the plot you can explain to show that the model is fit. Okay, okay, and then next step after you fitting the model, we will predict the yield on based on the regression model. Okay, so we get the optimal correlation for every parameter. Okay, so we get the optimal yield and the optimal condition for each parameter. Okay, for the predicted value, for the PHA yield of predicted value, so we want to know the predicted for the PHA yield for the dependent variable. So you have to use the prediction and then desirability and the model before this. Okay, and then first thing you have to install and call the library prediction and desirability. Okay, so first you have to install prediction. So just find prediction. Okay, and then install the desirability. Okay, and then you call both. Okay, and then you put the model that you get previously, but you have to take all whether it's significant or not. Okay, so you take all from the RSM. Okay, whether it's significant or not. Okay, so you take and then put it here. Before this, for the if you want to state the irrigation model in your thesis, you have to put the significant independent variable. Okay, but for this one prediction, you have to take all whether it's significant or not. Okay, so this one is just a name model in front one. Okay, then we want to predict for the PHA, so this is a name, this is according. Okay, the max, and then this the lowest and the highest in this one. Okay, the lowest one is 10 and then the highest one is 19.58. so you have to take the lowest and highest in your result previously. Okay, then predict outcome. See, it's a column model, how many column of parameter you have, and with the independent variable. Okay, how many parameter? 1, 2, 3, because we have propana, molasses, and then PHA. So that's 3, 0 here. And then we need to know the output, so we print the predict outcome. Okay, so I copy this into. Okay. So I print the so I get the predicted value for the PHA is 19.89. It's basically from the linear regression model. Okay, and then we want to know whether this output, the PHA yield predicted, how many percentage the desirability, the good, whether our predicted is good or not. So you have to find the desirability value. Okay, how many of the desirability. So I copy paste into the studio. Okay, so you get 0.98, that's mean 98% distributive value said that our predict value is correct. Okay, that's mean 0.98 is near to 1. That's mean our disability is strong. Said that this predict value is correct. Okay. After that, continue to predict the each parameter, the optimum value for each condition, molasses data. So you have to input the original data without the coded. Okay, this. Okay, so I save as secorder. Okay, my file name is named as secorder. So same as previous, you have to find the location and then the file name secorder.txt. Okay. Then I read table, I use the same name as previous because we already replaced. So you can use the same name. Okay. So after that, we have to model for each parameter. So if you have 3 parameters, you have to add on another model 3, LM. And then, okay, LM is the linear model. Okay, this one. And then mole, PHA. Molasses is our first parameter. Okay, mole and PHA. So this name you have to depend on what you key in the Excel. And the data secorder is the name of a read table. Okay, same model 2. So the second parameter, and then PHA dependent variable, and data our second our read table. Okay, so we have model 3. So you have the LM and then the another third parameter, the dependent variable, data. Okay. So make sure the name follow what you key in the Excel. Okay. So independent, dependent. So after that, you will get the optimum PHA from the previous. Our predict optimum PHA is 19.39. Okay, so this name is just a name, and then this the coding data.frame, and then PHA. So take what we key in the Excel. PHA, our PHA predicted is this a column, first column 19.39. Okay. Enter, and then we predict for each parameter. So model 1 with the new DF is our predicted PHA. Okay, model 1 for the first parameter, model 2 second parameter. Okay, and then we get for the molasses, model 1 is 43.81, and then for the propanol, model 2 is 1.801. Okay, that means these two value we get the predicted PHA 19.39. So for each we get the optimum value. Okay, so predicted optimum value for molasses, predicted value for the propanol. Last step, you have to do model validation. Okay, this is predicted from the RSM 19.39 with the molasses concentration 43.82, and then propanol concentration 1.01 with the desirability of 0.98 near to 1. Okay, so we have to do these two again with lab work. So we have to do the lab experiment work using this value of two independent variable parameter, and then we show my student get this value of PHA 19.55. That means, as you can see, the validated and predicted, the difference is small, 19.39 and 19.55. That means we get a correct value of optimum condition. Okay, so we have to do the experiment based on the predicted value, and then we check whether the optimum yield that you get with the experiment near with the predicted desirability value here. 19.39, 19.55. So this one of what is the highest value that you get, the first one. Okay, 18.63 is the 40, and 0.8 the highest in molasses and the propanol. So this is the final stage of the RSM. So you have to do model validation of the predicted value that you get. Okay, so after you get the predicted value, you have to do the experiment again. Okay, make sure you do duplicate to get the good result. So you do the experiment again, so you get this value. Then you compare with the predicted, whether the difference is small or big. If small, that means you have a good result. That's all for my part. Any problem, if you want to know more about the R software, you can contact me. I hope you still save my number. For today's class, I want you to submit an assignment, 2% per assignment. I want you to find the data from resources, whether from the senior or from your courses data that have done the optimization using different software. But I want you to use the R software to obtain the optimum condition and optimum yield. So you have to show all the steps and coding that used in the R software. So submit me to my email and due by 22nd November. Here my phone number if you have any question. So you can hear the example from your senior assignment. So you can show me the data that you use, and then step by step show me the step screening, CCD, and then find the RSM model. Okay, and then the prediction, and then the optimum value. Then after that you have to make the conclusion. Okay, so conclusion from the data from these are optimum you get. Okay, here the attendance link, and thank you.